Hi everybody, in this video we're going to continue our derivation of the eigenstates and the corresponding eigenenergies of the quantum simple harmonic oscillator Hamiltonian. That is, we're looking to solve this equation, the time-independent Schrodinger equation, and find these eigenstates and the corresponding eigenenergies. The quantum simple harmonic oscillator Hamiltonian is just a Hamiltonian with the simple harmonic oscillator potential energy function in for the potential energy. All right, so first let me go over our previous results so far, which takes us down to 2. So our first step was to rewrite the Hamiltonian. So we defined some operators, call them A plus and A minus, which have this form, where x is the position operator in one dimension and p is the momentum operator in one dimension. With these definitions for A plus and A minus, it turned out that we could rewrite the Hamiltonian in this form. So there's really 2 equations. We can look at the top signs and we can look at the bottom signs. All right, so that was step 1, rewriting the Hamiltonian. Step 2 was really important. Step 2 was to prove the following proposition. If psi is an eigenstate of the Hamiltonian with corresponding energy eigenvalue E, then the state constructed by operating on psi with A plus is also an eigenstate of the Hamiltonian, but with h bar omega higher energy. Likewise, the state A minus operating on psi, now that's another state, that's also an eigenstate of the Hamiltonian, but this time with h bar omega less energy than that of the original state that we were talking about here. All right, so why is that important? Well, if we could just find one solution to this equation, one eigenstate and corresponding eigenenergy, then we could construct all the rest by either going up to higher energy states with the A plus operator or to lower energy states with the A minus operator, and we could find the corresponding energies by adding or subtracting increments of h bar omega. In principle, well, in practice what we want to do, the easiest way to go, is to find the lowest energy state, the so-called ground state. If we could find that, the eigenstate of this Hamiltonian with the corresponding lowest energy, then we could construct all others by successively operating with the A plus operator. So we could operate with it once, put n equal 1 here, we get the first state above the ground state. It'll have h bar omega, 1 increment of h bar omega more than the energy of the ground state. We get the next one by operating with this twice, so have n equal to 2 here. We could then have 2 here, so we'd have 2 increments of h bar greater than that of the ground state energy, and so on. Note I've just put a sub n here to represent a normalization constant. So this will give us the wave functions, the corresponding eigenstates, aside from a normalization constant, which we could then go find in the usual way. All right, so with 1 and 2, that gives us the scheme 4 to get all the eigenstates and corresponding energies of the quantum simple harmonic oscillator, if only we could find the ground state. So that's what we're going to do now. Now, there's got to be a ground state. There's got to be a lowest energy state because this is a bound state problem. So we'll call that psi sub 0. Now, if it's the lowest energy state, that means we can't go lower in energy. So the A minus operator, which should take us down energy, operating on this, will give us 0. That's basically, if this is true, that's basically the definition of the ground state. It's the lowest energy state. Okay, so now our process is as follows. Let's just plug in the A minus operator here, solve the corresponding differential equation, and it is a differential equation because remember the momentum operator has a derivative in it, and then we can solve that differential equation and hopefully get the ground state psi sub 0. So here we go. We're going to plug that in right here. All right, now let's remember that the momentum operator has the following form. And I've changed the partial derivative to a full derivative since we're working in one dimension and there's no other independent variables running around other than x. All right, so We can multiply both sides by this square root factor, so it'll be gone from here, and 0 times anything will give us 0. I times minus I gives us 1. So we'll have h bar d dx psi sub 0 plus m omega x psi sub 0 equals 0. So let's write that out. We can take this to the other side of the equation. And I've also divided both sides by h bar. All right, now what we can do, we've got a first order differential equation. We can solve this by getting all the psi sub 0 stuff together and all the x stuff together. So let's do that. This is something that we know how to integrate. So we'll just integrate both sides. On the left-hand side, we have the natural log of psi sub 0 plus a constant, which I'll just take the constant over to the other side, combine it with the one on the other side. On the right-hand side, these constants come out, and I'll have the integral of x dx. Well, integral of x dx will just be x squared over 2. So we get this, where I've added the constant of integration, and that's really the constant of integration from both sides, just combined over in one place. All right, so now we need to get rid of this natural log. We can do that by putting it in the power of an e, but we've got to do that to the right-hand side as well, so here we go. And on the right-hand side, I've used the fact that if I've got e to this plus this, that will be e to this times e to this. All right, so we're just about done here. We can note that this is just another constant. We'll call it a. And so here's our result. E to the natural log of psi sub 0 is just psi sub 0. And on the right-hand side, we've got a constant. And this stuff. And we're done. So we found the lowest energy eigenstate of the Hamiltonian. The only thing we need to do now is find the corresponding eigenenergy. And it turns out we can do that just by plugging back into the time-independent Schrodinger equation. So that's what we'll do next, but first I've got to clear the board. Okay, so let's plug this into the time-independent Schrodinger equation. I've put an E sub 0 subscript on the eigenenergy to just indicate that it's the corresponding energy going with this state psi sub 0 that we just found. All right, so what we can do now is plug in for the Hamiltonian and see what comes out. Now, let's be clever. If we plug in with the Hamiltonian, but the form of the Hamiltonian that comes in with this A minus, that will simplify part of our expression here, our equation, because A minus operating on psi sub 0 will be 0, by definition of this being the ground state. So let's plug this in using the top signs and see what emerges. All right, let's distribute this on through. All right, so here we see what we're talking about. A minus operating on psi sub 0. That gives us 0 by basically definition of that being the ground state. So that's gone. So this is gone. H bar omega times 0 is 0. So I've got 1/2 h bar omega times psi sub 0 equals E sub 0 times psi sub 0. Psi sub 0 is the same as psi sub 0, so E sub 0 has to be 1/2 h bar omega. Great. So now we have the eigenstate corresponding to the lowest energy, and now we know what that lowest energy is. So going back to our scheme here, as I said before, we could generate all further eigenstates by successively operating on the lowest energy eigenstate, with additional operations of the A plus operator. We can then finally also get this E sub n. So the energy of the nth eigenstate will be n times h bar omega plus 1/2 h bar omega, or we can put it in this nice form, factor out the h bar omega, and we'll have n plus 1/2. So this is the form you usually see the energy of the nth eigenstate of the quantum simple harmonic oscillator.